All right. So yeah, since I'm the last speaker, there will be some correlations with the previous speech, or I should rather say some mutual information, and you will see why during my talk. But I hope I will also transmit some unique information. So as you see in the title of my talk, we started to work on DeepSDMs like 7 years ago in the context of the PhD of Christophe Bottella. So the PhD topic was not about that, it was about bias in sampling efforts. But since we had like skills in the team and about deep learning, we thought it was a good opportunity to also try this kind of model. And because we knew that trying to learn representation, so representation learning provides a lot of benefits on any problem. And so we believed it could be a good idea. And so we just took a classical species distribution model and we replaced the input variables by some learned representation. And in this very first study, the two interesting conclusions were that the more species in the model and the better the performance were, so which is fine because it means that there is some information exchanged between the species. And and the other main conclusion was that the species that benefit the most from the performance gain were the rare species, and this has been confirmed in many other studies afterwards. So the gap in performance compared to classical model is not huge, but there were these two interesting things that make us want to continue working on the problem. Then in the PhD of Benjamin Deneux, so we tried to understand better what kind of information can be captured by such a model. And so this was this study about trying to show that the spatial information provides some additional predictive performance to the species. And so this was done through an ablation study. So you take the spatial patches of the bioclimatic variables, and you randomize the pixels, or you take the mean value, or you try to only keep the structure without the value of the signal, and you measure the performance of this different strategy. And so you can see that really this spatial structure brings some significant performance gap on this. And and then the same story happens on temporal structures. So during the PhD of Joachim, where we were using time series of satellite images, and also with an ablation study, we were able to show that having the full time series improve a lot the performance in this model. And and somehow it captures the phenology of the habitats. So, another lesson is that somehow such DeepSDMs models are very good in extracting relevant ecological information from any high-dimensional raw data. I mean, that's really where deep learning is relevant. It does not suffer from the dimensionality curse, which is one of the main problems of many models. And many other speakers talk about that, but I like this simple illustration that is just you train a model on satellite image, you project the feature space in 2 dimensions to visualize it, and then you color this space with the temperature, the average temperature of that location. And as you can see, it's highly correlated. And all this feature space is structured with this temperature information. So that means your model is able to learn the temperature just from an image, and just because you provided it some species as entry. And so that's somehow a way that illustrates that such models are very powerful in extracting the information that is available. This Benjamin talked about the same story, but another visualization that shows that. But it does not mean that any raw high-dimensional data is always useful, so, which is another story. And yeah, one example is, for instance, you start with a model trained only on Sentinel-2 images, for instance. Then you are happy, you have good performance, and then you add like other classical variables into your deep learning model, and so you improve the performance. And then finally we had a big model with all the variables that works well, and we just tried to remove the Sentinel-2 image from the model, and then, oh, as you see, it's almost equivalent as with or without the Sentinel-2 variable. And so let's have like an information theory perspective of that. So yeah, we talked a lot about variables, concurrence. I mean, since we are not in the linear world, but in the non-linear world, I think information theory is sometimes better to explain what happens. So let's consider a DeepSDM with 3 modalities. Any of them. Each modality has an encoder and then some shared layers. And you have a task that is to predict species, since we are on species distribution modeling today. So this is an information theory perspective. So you have your Y, your species that has some entropy, some information, and you try to capture this information. And you have 3 modalities. So each modality contains different quantities of relevant information with more or less overlaps. All right? And for instance, this part is the information about Y that is contained only by X1. No, that is contained by X1, sorry. This is typically what you can get if you train a model only on this modality. And since if you use DeepSDM, they are very good in extracting all the information that is there. That's the powerfulness of this method. And on the other side, this is the information contained only by X1 about Y, all right? And to measure this one, it's a little bit more complicated, but you can imagine you have a model with all modality, you remove this modality, and then you have the modality-specific information, quantity of information of this modality. All right? And of course, there are some quantities of information that are shared by different modalities. And for instance, here, it's the quantity of information that is contained in any of these modalities, all right? So in some cases, as this one, sorry, all modalities are useful because they all have some unique information, as you can see, the plot. And so if you look, like if you have this kind of plot, so the blue modality, you could say, okay, the bottom is the specific information to this modality, so the unique information, and the top of the bar is the total amount of information that this modality can capture. And so here, all 3 modalities have some unique information, so if you combine the 3 of them, you have a gain and you're happy. And yeah, and if you had all modalities that capture all factors, you could reach your upper bound, that is the entropy of Y. But sometimes, not all modalities are useful, such as in this example. So if you look at the pink modality, so it contains a lot of information about Y. But as you see, all the information it contains is also covered by the other ones. All right? And so if you look at the blue one, let's say climatic variables, they have some unique information, total information, another one, unique, total. And imagine the pink one is maybe the satellite modality. So it's the one that contains the highest information. So it's an example. But it has no unique information. So it can capture the temperature, but maybe it does not contain any new unique information because in your other rasters, you already have many data extracted from remote sensing and so on and so forth. And so, yeah, choosing the right modalities, I mean, it's a complex problem. So with techniques like Davis showed this morning, you can try to quantify all those different quantities. And yeah, there can be other techniques to do that. And so, but that's typically the kind of problem we address in this GeoLife Clef challenge, where we provide complementary data. We try to make them, as complementary as possible. And this multimodality problem is what we want to evaluate in such challenge. And so we let people play on such data. We provide big amounts of occurrence data, from big amounts of presence-only data, but also some presence-absence data. And we provide different modalities, such as the satellite images, the satellite time series. So here it's punctual, but we have 20 years of Landsat signal at the quarter level. And climatic time series, like 40 years of climatic samples. And so the baseline model that we shared, and which was also used by the winner to improve performance, is an ensemble of those three kinds of data. And so the time series, we encode them as an input of the model in forms of cubes. So it's cubes of months, years, and then the variables. All right? And so it allows you to apply. On the left, you show that the yellow peak, of course, is the summer. And so, you have a tensor that contains your time series. And it's the same for the satellite cube. The satellite image is an image. And so as you see, the variable that contains the most information is the satellite cube, so the satellite time series, the Landsat. I think it's very interesting because in all previous studies we had, it was always the bioclimatic variables, ever. So that was very interesting to see that here. It's, the satellite time series. So maybe it captures the history of the vegetation. So it was a land and then a forest and then something else. And this matters a lot on what species you have in the end. Or maybe it captures some information about the soil, which is the hypothesis of Florian when we discussed yesterday. So I talked a bit about the X. So what about the Y? So of course, with DeepSDMs, we can handle all tasks as in classical SDMs. So you can predict abundance or presence absence or presence only. Here we see that presence only is a very weak information data. So you only have one component of a big vector of 50,000 species if you consider big models. And so presence only is biased, but it's also very weak in terms of information compared to community data. So what can we do with deep learning regarding Y? One first thing we have been exploring is transfer learning. So you train a model on presence only data because you have a lot, and then you can fine tune it on other tasks, so like abundance data. So this is what we did on fish species in the context of the Fish Predict project managed by David. And then we compared to a random forest here. So the important information is that the abundance data, it's very small. It's only 400 sites, all right? So you have very few data. And so if you train a deep learning model without transfer learning on this data, it doesn't work at all. It's very bad compared to the random forest. Or it's not very bad, but it's less performant. But then if you use the transfer learning, of course, you will really reduce the variance a lot. And this is what it allows you to have a gain in terms of performance. So what can we do else? So we already talked a lot about it, community and species interdependencies. But my view of it is that Y is also a complex signal, all right, in terms of machine learning and information theory. And so same story, you have different species and each of them have some mutual information and some of them are maybe unique information, but whatever, it's a complex signal, it's not linear, so matrix, low rank matrix decomposition is very interesting, but maybe it does not encode all the complexity of those dependencies. And so here again, if you do some deep learning, you will try to also learn a representation from this signal. And so, basic views, like you will have an encoder for Y and an encoder for X, and you will do some join model. So it's like deep join SDM. So Sarah had a slide like doing something like that, I think. And so in our case, we worked only on the encoder of Y, so independently from the X. So just to see if we are able to like better encode the signal contained just in the species assemblages. And so this is the work of César Leblanc, so a PhD student in the team. And so it's called plant BERT. So it's also using the BERT principle, so those masked long-range models. So here you will rather mask a species and you train the model to predict which species has been masked, all right? And you do that on a big data set of species assemblages. So in our case, we used the EVA, so use the European Vegetation Archive. So it's almost 1 million of plots in Europe with all those species. And since it's a long-range model, we will try to learn the syntax of those assemblages. And so the species are sorted, and they are sorted by decreasing dominance, all right? So I won't spoil all your talk of tomorrow, César, but since tomorrow we have a smaller event, sorry, where César will present that. So what we can see, so we compare just the performance of predicting the species. So how good we are to just predict the species that has been masked. And so as you see, you can reach accuracy like 16%, which is not a lot, but it's much more than just the co-occurrence approach. So it's a naive Bayes model where you just predict the probability of the species conditionally to the others with an independence probability hypothesis between the other species, but and it's also much better than just using other classical machine learning model. And if you look at the performance of predicting the missing species depending on the rank, so the first one is the most dominant species, the second one is the second most dominant, third, etc. And so each time you just remove one species and you look at the performance depending on the rank. So the first one is the most easiest to predict. So that means that if you know all other species of the assemblage, it's not so hard to predict the most dominant one. And the hardest one is the second one for the plant BERT model. So if you look at the other models, they are all decreasing based on the rank, but an interesting pattern appears with plant BERT where you see that the second one and the third one are more hard to predict than the rest. So that means that somehow if you know the first, the second, and the third, you maybe know what the habitat is now, and now it's more easy to predict the following ones because they are structuring the habitat. And this was not happening with the other model because maybe it's a pattern that is hard to capture. And then you can also use this model to do some fine-tuning and habitats in particular. And and you can also improve the accuracy of this habitat classification. And here again, we can study if you remove some species in the assemblage, if the accuracy drops. And so here you see the number of species removed from the assemblage, and if we are still able to predict the habitat. And so, of course, if you remove all the first species, so if you remove the first three species, the prediction will be very low. And at the opposite, if you remove the last species, you're able to predict the habitat. You are still able to do it. I think I'm almost done. Maybe, just a few words about GeoPlantNet. So maybe some of you have seen the demo of Rémi at lunch. But we are applying all those deep learning model to build maps at the European level. So it's at 50.50 meter cells. And so this required, implementing a big framework by Rémi, who is in the room. And then you apply your DeepSDM and also the habitat classifier model of plant BERT. and you are able to like predict species maps. So we have it for like all species in Europe. So similarly to what Philippe presented, you have like capabilities of browsing, selecting polygons, and computing some indicators on the results. And you have that for species and also for the habitat, so for the UNIS habitat. So the URL is open now, so you can play with it, and we are really looking for feedbacks about it. So it's the version 1 of the maps, and the version 1 of the maps, it was mostly satellite images, and as I told you in my talk, it's not the more informative, and we are currently building the V2 of the maps, which will have all the cubes I was explaining, so the Landsat cubes and all that stuff, and so probably the maps will be better. But so it's still open to also play with feeders, the functionalities, and we try to collect feedback also on the robustness, the speed, and things like that. So that's it. Thank you very much.
Thank you, Alexis. Some questions?
Thank you, Alexis, for the great presentation. I really enjoyed the information theoretic perspective, and I was wondering, wanted to have your opinion on the difference between what you were showing and the explainability tools like SHAP values, where you can have a partitioning of the information that is brought up by each modality.
So clearly Shapley values are what the kind of information they are trying to capture. So because they remove one modality and check the unique information of this modality compared to the other. So here it's more general point of view in terms of theory of information, because it's easy also to display, because you can have those bubbles. And but clearly Shapley value are inspired by such a theory, by information theory, clearly.
Except here, in your case, you need to train different models with different modalities, whereas with...
if you really want to have the real quantities here, you are obliged to train a lot of models, or maybe with models such as Davis presented, you can do it only at inference. But on the output, you need to measure like the entropies between the Y and the predicted Y. But you have ways to estimate most of the pairwise quantities, but if you have too much modalities, then it starts to be combinatorial, and then you are dead. So this is where models like the one of Robbins, Binden, and Davis can probably help to do that. Because even with Shapley values, you have this combinatorial issue at some point.
I guess you have to do it at their embedding levels and not on the raw data. Thank you.
Another one.
Thank you for this very interesting overview. I was particularly excited about the LLM, because the idea is very similar to the recommender system I presented earlier, just with a modern tool, and also with much better data. You have shown how predictive skill varies as a function of the dominance of the species. I was wondering whether you have also done experiments where you increasingly remove information. Is that something that decays fast if we have half the community muted, or how does it behave?
We see it a little bit on the habitats, not on the species, but I think it would be pretty similar. But here we really remove one, then two species, then we remove three, then we remove four. The blue curve is you remove the first species, but the orange one is you remove random number of species. So this gives you an idea of the slope for the first 5, but then you could continue. So it really depends on which species you remove regarding the habitat prediction. And for the species, as you see, the curve is slightly different. So here it increased, but of course it then re-decreased after. Cesar, you confirm? But it remains stable. It remains a bit stable. with up to how many species, do you know?
I will say tomorrow. I don't remember.
So, but please talk with Cesar at the break. Maybe he will provide you the information if you are not here tomorrow.
Thank you.
About the GeoPlantNet, do you allow the user to download rasters, or
so there is a WMS web service that will allow to access to the data in forms of WMS. The rasters are huge. I mean, you cannot just download it like a TIFF file because it's very, very huge. We are maybe trying to fix that for the future, but yeah, so far with the current infrastructure, it's only WMS, so you can download parts of it easily. Entire TIFF, we did it for some species, for some partners. I mean, you can also contact us, but it's not directly possible in the tool right now. Yeah. But maybe with EBV portal, or we have to discuss with other infrastructures to see if we can share the rasters there. So. But yeah, there is no licensing issue anyway. Yeah.
I have another question on GeoPlantNet. Do you include a seasonal variation like does Philip? I mean, probability of seeing a species depends on the month or the day or the season?
And no, for now we were only on the spatial interpolation phase. And of course, the next projects where we are looking funding for will be like to run such model every year, and also to include temporal information at a finer scale. But since all is very huge, we had the choice to make between spatial resolution or adding temporal information, and somehow we choose the spatial resolution in terms of trade-off. Yeah.
Thank you. Time for coffee break.
Thank you.